Hey everyone, welcome. Today we're diving into something really cool, physical AI. We're going to lay out the entire roadmap, a learner's journey, for building robots that do more than just follow commands. We're talking about robots that can actually think and interact with the world around them.
All right, so let's just jump right in with the big question, right? How in the world do you teach a pile of motors and sensors to think? I mean, it sounds like science fiction, doesn't it? But this is the absolute core challenge of physical AI. And the cool part is, the path to solving it is actually way clearer than you might imagine.
Okay, so before we get into the how, we've got to cover the what. So what exactly is physical AI?
At its heart, physical AI is just the convergence of artificial intelligence with the physical world. So think about it this way. This isn't about AI living on a server somewhere in the cloud. No, this is about robots that are out here with us, perceiving, reasoning, and acting in our messy, unpredictable, real-world environments.
And really, it all comes down to the super simple but really powerful three-step loop. Step 1, the robot perceives its environment. It's using its sensors, cameras, LiDAR, you name it, to take in the world. Step 2, it processes all that data. The AI brain kicks in, interprets everything, and plans its next move. And finally, step 3, it acts. The motors fire up and it executes those commands to move and interact. Perceive, process, act. You've got to remember that. It is the fundamental heartbeat of every physical AI system.
Okay, so we've got the what down. Now for the fun part, the how. We're going to walk through this whole journey in 4 main modules. And module 1, well, it all starts with the foundation. We're literally building the robot's nervous system.
So what is this nervous system made of? Well, it's built using something called ROS2, that's the Robot Operating System. The best way to think about it is like a universal language that lets all the different parts of the robot talk to each other. You've got these things called nodes, which are basically little programs for each component, one for a camera, one for a motor, and so on. And these nodes communicate over what are called topics, which are kind of like public broadcast channels for all that data. We'll be using Python to write these nodes, and then we'll create something called a URDF model. That's just a fancy way of saying we're building the robot's digital blueprint, its anatomy chart, that spells out exactly where every single joint and sensor goes.
All right, so once that nervous system is in place, you need somewhere safe to actually test it out, right? I mean, you definitely don't want your brand new, probably expensive robot just plowing into a wall on its very first run. And that's exactly where Module 2 comes in. We're going to build a virtual playground for our robot.
This whole stage is all about creating a digital twin of your robot and its world. You'll use tools like Gazebo, which handles all the physics, so if your robot drops something in the simulation, it actually falls realistically. Then you get to build out the whole environment, the rooms, the furniture, all the obstacles. You can even use game engines like Unity to make it look super realistic. But the most important part? Simulating the sensors. This makes sure the robot's AI is getting the exact same kind of camera feeds and laser scans that it would in the real world.
And this comparison here just nails why this is so critical. Look, in the virtual world, it's a total sandbox. It is completely safe to test your craziest ideas, and you can iterate at lightning speed. You can fail, learn, and try again in minutes. But in the physical world, yeah, it's unpredictable, and mistakes have very real, sometimes very expensive, consequences. This is why digital twins are absolutely the key to getting it right in the real world.
Okay, so let's recap. We have a nervous system, we have a safe playground to test it in. Now it's time for the magic. Module 3 is where we build the honest-to-goodness AI-powered brain that's going to drive this whole thing.
This is where the deep learning really kicks in. We'll use simulators like Isaac Sim to generate tons of what we call synthetic data, basically perfectly labeled images to train our AI so you don't need to spend ages with a real camera. Then we plug in perception models to help the robot actually recognize objects. The next piece of the puzzle is something called Visual SLAM. This is so cool, it lets the robot build a map of a room while at the same time figuring out where it is on that map. And once it has that map, it can use a planner like Nav2 to calculate the smartest way to get from point A to point B.
And that brings us to our final module, and honestly, this is the most exciting part, where everything we built just clicks together. In Module 4, we're going to connect all the dots and go from a simple spoken command all the way to a complex physical action.
Yeah, this is where it starts to feel like the future is here now.
First, we use a system to take a voice command and turn it into text the AI can work with. Then we bring in a large language model, an LLM, to do the cognitive planning, so it can take a vague request like, hey, get me a drink, and actually reason about what that means and break it down into concrete steps. Then powerful computer vision models help the robot actually find and identify the specific object you asked for. And the capstone, the grand finale of this whole journey, is putting all of this together to build an autonomous humanoid that can actually understand what you're saying and act on it.
So, there you have it, the 4-part journey. Now, I know it might sound like a lot, but having a really structured path makes it so much more achievable. So let's talk for a second about why this kind of hands-on, step-by-step approach is the best way to learn this stuff.
Well, first and foremost, it's all about progressive learning. You start with the absolute basics, the fundamentals, and then each new topic builds directly on what you just learned. You're never just thrown into the deep end. It's about building a really solid foundation of knowledge one step at a time.
And it's super hands-on. You're not just reading dry theory. You're getting actual code that you can copy, paste, and run immediately to see how it works. It's all about learning by doing.
You know, visual aids are also a huge help here. Really complex concepts, like how a robot's navigation system works, are broken down into these super clear diagrams and flowcharts. It just makes everything click and so much easier to remember.
And at the end of the day, the whole point is to build real things. The focus is always on practical, hands-on projects. You're not just learning some abstract theory, you are applying every single new skill you learn to build actual robotic systems, right from the ground up.
So you see, this journey, from a simple pile of motors and sensors to a genuinely intelligent, interactive robot, it isn't black magic. It's a structured, learnable path that anyone can follow, which really just leaves one last question for you to think about. Now that you know the path, what intelligent robot would you build first?